Hi everyone. Okay, so I understand that Lenz's law is kind of a tricky one. So what I'm going to do for this key is instead of just posting it on the internet and having you try to figure out all my handwriting, I'm just going to do this live. So, let's say I'm sitting down to do my homework. I'm looking at homework 10.5, Lenz's law, and the idea with this homework is just to practice this one law about physics. So, let's get started. Number one is a question that's easier than it looks. So we've got this conductive bar, it's moving to the left. The key part of this question is that the current is going counterclockwise. So when it's asking about the induced magnetic field, we should probably add that's the induced magnetic field. Well, that must mean that its field goes along with the current. So applying right-hand rule number 2, fingers curl in the direction of current. That puts my thumb out of the screen towards you guys. That means the field must have been in the Z direction, positive Z direction, or out of the page, E. Okay, number 2. We've got this uniform magnetic field with a resistor, wire, loop, etc. And it's asking which of the following changes will create a current in the resistor. So, let's take a look. If I use Faraday's law, I just need to change the flux in some way in order to get a voltage, and the voltage would result in a current. So, flux, that would be BA cosine theta divided by time. So, I could change the area, that's 1, I could do that. I could change the magnetic field, that's B, I could do that. Hey, C also changes the magnetic field. That would also give me a voltage to give me a current. So, the answer must be E, all of the above. Normally, I'm only going to give you problems where it's already the correct orientation, so for the most part, we ignore this cosine theta. But I guess if I changed theta, that would also change the voltage, and that would also create a current. So check all of the above, E. Number 3, long straight wire. We've got a conducting loop, wires carrying current, and it wants to know if the wire is suddenly moved toward the loop, what will happen? So let's take a look at this picture. Currently, you see what I did there? Currently the field due to this wire, I'm pointing my thumb in the direction of current, right-hand rule number 1 says that I have into the page field due to this wire. But the farther I go away from this wire, the weaker that field is. So if I move the wire toward the loop, that will give an EMF. It can't be A. Because in my equation for Faraday's law, I am changing the flux. I'm changing the field, even though I haven't changed the area. In this case, I'll be changing the field by increasing the field. And remember by Lenz's law, if the field is increasing, that means the induced field is in the opposite direction. So, in this case, the increasing field, the opposite direction of the existing field, would be dots. Finally, putting my thumb in the direction of the dots, out towards you guys, my fingers are going to curl counterclockwise. So, what am I looking for? In my answer, I'm looking for something that has a current counterclockwise. So that would be D. But let's just make sure the other answers don't make sense too. B could occur if there were a break in this wire, but there's not. Because there is a voltage and it's a closed loop, there will be a current of some way, shape, or form. C is a fine choice except the direction is backwards. And E, an induced electric field that is clockwise around the loop. Electric field is kind of irrelevant to this conversation, so this, if I see electric field instead of current, is not really an important part here. Okay, now, every year, this is my favorite question because, one, let's check out this picture for number 4. I'm pretty sure I told you guys to do exactly not this. So we got a bar magnet, a ring, and actually in this picture, the bar magnet's not falling at this person's eye, but the ring is. How silly is that? Okay, anyways, as the ring falls, it has a big magnetic field when it's close. Remember, magnetic field goes from north to south, so imagine it doing one of these things. And it's going to be experiencing a decreasing magnetic field. When it's a decreasing magnetic field, it's going to put a induced field in the same direction by Lenz's law. So, what's going to happen with the current here? I'm going to put my thumb in the direction of the field, which is not super comfortable, so bear with me. And that puts a current that's going, wow, you can't see that at all, like this. It's going in this direction. Now, what the person would be seeing involves a little bit of orientation. So imagine now the person is staring at this loop. They'd be seeing current going out of the page over here, into the page over here. So if I imagine rotating it, this person would be seeing an induced current going counterclockwise. That's A. And let's just make sure the other answers don't make sense. We know there's going to be some sort of current. So we know it's not going to be C or D or E. I'm only choosing between A and B. Because the magnet is stationary, that doesn't mean there isn't going to be an EMF. There's an EMF because the field is changing as the loop falls. So it can't be C, D, or E, and B is just in the wrong direction. No big deal. Number 5, sheet of copper pulled at a constant velocity from a region. Okay, as this thing is going, it induces a current that's going around counterclockwise. That must mean that its induced field is out of the page towards you. So I'm going to draw these as out of the page towards you. The induced field is out of the page. But since this was decreasing area, as this goes, the area that's enclosed in this loop gets smaller and smaller and smaller. Decreasing area meant that this induced field must be in the same direction as the original field, meaning this must also be dots. So the original magnetic field in all of this area must have been directed out of the paper. D. Okay guys, we're getting there, halfway through. More than halfway through. Okay, number 6. So we've got a wire moving through a magnetic field directed into the page, and it induces a charge separation. Notice that there's no current in this. There's no current in this one because we have the separation of charges, but it's not a complete loop, so the charges can't just go around in a circle here. Okay? So, in this case, we're trying to figure out which way the wire is moving. We have a field that's going into the page direction, a charge separation in this direction. So if you wanted to, you actually don't even need to use Lenz's law for this. So in fact, let's not. Let's use an earlier one. Because of the movement, so we're trying to figure out what direction the velocity is. We know the direction of the force on the positive particle. The positive particle moved to the right. So the force on the positive particle was in the x direction. The field was in the z direction. Well, technically the minus z direction was into the page. That must mean the velocity is either in the y direction or the negative y direction. And if we right-hand rule this by putting my fingers into the page and pointing my palm to the right. Ooh, let's see if I can do that and still be in screen. All right. That means my thumb has to point down towards the bottom of the page. So that would be the negative y direction for velocity. Toward the bottom of the page, that's E. For 7, in each of these situations, a bar magnet is aligned along the axis. It's asking which one will not induce a current. So what I need to do is I need to have closed loops. So I have 5 closed loops. That's not going to be it. Right? And I need to be changing either the field or the area over time. If I look at A would be experiencing an increasing field. So it would have a voltage, it would have a current, not A. B, they're moving towards each other. So the loop would experience more field in the next moment. It would be having a changing field, so it would have a voltage, so it would have a current, not B. Okay? C, same business. If the wire is moving towards the magnet, increasing field, has a voltage, therefore current. It's easy. D, they're moving towards each other, has voltage, has current, so it's got to be E. And if you look at it, that's because they're both moving at the same speed relative to each other. This North Pole is going to make a field that the coil experiences constantly. Since B is not changing, our induced EMF would be 0. So 7, E. 2 left. Okay, we've got 8. Magnetic field decreasing with time is pointing out of the page through a loop of wire. This is just 100% simple Lenz's law. Keywords, field is decreasing. That means flux is decreasing. If flux is decreasing, Lenz's law says that means our field is induced in the same direction as the original. My induced field will be dots. Out of the page, same direction as the original. Stick your thumb out of the page, current is going counterclockwise. A. Finally, number 9. For this one, I have 2 loops of wire, and we're trying to figure out if they have any induced electric currents. So I'm going to do the easy one first. Loop 2. Loop 2 experiences the same field in this position as it did a moment beforehand. Because it's the same distance from the wire, loop 2 experiences the same magnitude of field 1 moment in the future. Whatever my answer is, loop 2 should have no current. So that only leaves, at this point, A and C. So it's not going to be B. That makes my life easy. So now I'm choosing for A, or loop 1, between no current and clockwise. It turns out I don't even need to do the rule for this. I know that as this wire gets pulled away, this wire loop gets pulled away from the original current carrying wire, that it's going to experience less field. According to our first field equation, the farther this is away, the less field there is. Loop 2 is experiencing a changing flux, and therefore has a voltage, and therefore has a current. It must be C. The end.